So in the following minutes, I'm going to share with you the initial benchtop results of the impact of stent retriever dip design on distal embolization during mechanical thrombectomy. So these are the disclosures related to this study. And what we already know is that the factors affecting the procedural outcomes are the repeated number of passes, the clot fragmentation, and the distal embolization that lead towards both angiographical and clinical outcomes. So what we aim to do in this study is to evaluate the efficacy of different stent retriever distal dip designs to prevent procedural distal embolization. We are studying these 3 treatment arms. First, it's a Solitaire 6x40, which is the open dip stent retriever, the Embotrap 2 5x33 as the closed dip stent retriever, and finally NEVA NET 5.5x35, which is the filter dip stent retriever. The first 2 devices were delivered through a 021 microcatheter, whilst the last one was delivered by a 027 microcatheter. The technique we're using is the conventional stent retriever and balloon guide catheter, and we performed 30 cases per each treatment arm. So the primary endpoints of this study were the rate of the first pass recanalization and the distal emboli parameters. This is the experimental setup we used to perform the experiments. It includes a 3D printed neurovascular model featuring a complete Willis polygon, and it was connected in a four-loop setup with 2 filters, 2 micropore filters of 100 microns. So there's one filter placed in the inflow to prevent foreign particles from getting into the system, and there's another filter placed at the outflow of the system to collect all particles that is generated during the procedures. And then to simulate these occlusions, so before performing each experiment, we can see this close-up on the model and the Willis polygon where we embolized a stiff friable clot analog to reproduce the most challenging scenario where there's a low stent retriever and clot engagement and the clot is fragment-prone. So in all cases, we simulated this N1 occlusion at the right side, right after the curve, marking yellow of the 120 degrees of curvature. And we only performed 1 attempt per each case, so because we were going straight forward to assess the first pass recanalization, and here's an example of the initial occlusion, and an example of a successful first pass recanalization, which is a non-remnant occlusion detected in the initial occlusion site, either on the distal branches of the same territory or new territories. And then the right side, you can see an example of the failed first pass recanalization. Now, to assess, to characterize a distal emboli, what we did is after each experiment, we took out the filter here, and then we acquired the images of this filter, and then this image was further processed with an algorithm that provides the following the information here: the largest distal embolosphere diameter, the total count of large emboli, which are those above 1 millimeter, and the total count of distal emboli. Now I'm going to share with you the results of the benchtop testing. To begin with, about the first pass recanalization, in our in-vitro thrombectomy model, we found out that the filter dip stent retriever achieved a higher rate of success in comparison to the open stent retriever and the closed stent retriever. And there are several factors that can be conditioning the difference between the success rates. And this might be, for example, the diameter and the length of the devices, also the mesh structure that provides different kinds of interaction between the clot and the device. In case of a NEVA NET, would be the drop zones. In case of the Embotrap, would be the articulated, fragmented design. And in case of the Solitaire, would be the tubular structure. So, but in our experience, what we think that it's influencing more on this success rate positively for NEVA NET is how the microfiltration net located at the distal tip is interacting with the clot. And here there are some videos showing how the net is actively engaging the clot and retaining against the impaction pressure of the flow and dragging it through those segments of this model. And here's a close-up so you can better visualize the interaction. Now the results concerning the distal emboli, starting with the total amount of emboli characterized, we found out that there's no significant difference between the three treatment arms. And this also means that using 027 microcatheter does not have any adverse effect on the overall total count of emboli during the experiments. If we look at the other two emboli-related metrics, we have the maximal fair diameter, and we can see that the filter tip stent retrieval reduces this parameter, which means that the clots migrating, the fragments migrating distally are smaller in case of this treatment arm rather than the other two. And the same trend is present in case of the total count of large distal emboli, where the filter stent retriever almost did not generate any particles larger than 1 millimeter, whereas the other two arms did. So in conclusion, when facing fragment-prone clots with low stent retriever engagement, the microfiltration net has two main functions. The first one is to reduce the frequency of large clots that embolize distally during a procedure, which potentially could mitigate the deleterious effect of the distal embolization. And the second function is that the microfiltration net might increase the engagement and drag the clots in the those basal segments. Finally, initial benchtop results show that the stent retrieval distal dip design entails a quantifiable impact on mechanical thrombectomy procedural success. And that's all. Thank you.
Ali.
I do have a question. So I did notice that you have set up the pump at about 800 cc's per minute.
Mm-hmm.
And I assume that is going through both carotids of the model.
That's right.
First question, why did you pick 800 cc's? And the second question is that have you done any experiments with the lower flows? Each carotid normally should have about 200, 250 cc's per minute normally. 800, assuming running on both carotids, seems to be a little on the higher side. So if you have done any experiments with the lower flow, would that result in come up with different results?
So thank you for your question. So we chose 800 cc because there's the common setup for the in-vitro experiments that is in literature, but there's also another factor, that is that this model is not compliant, our 3D model is not compliant enough to simulate the both systolic and diastolic pressures. So to compensate the lack of the realistic pressure, we increased the flow in this case a little bit. Mm-hmm.
Any other questions?
So you saw that you could prohibit the large emboli, but to me, isn't the big problem the small ones that you don't see? I mean, I don't like to lose any fragments, but if I am to lose one, at least if I could see it, I had a chance to do something about it. But the problem to me is that all the small fragments, regardless of technique, that you lose and you cannot do anything about it. Is there any way that you can foresee that we could prohibit also to lose these very small ones that we even don't see?
Well, in this case, since our setup was made to measure those emboli larger than 1 microns, we're not taking into account those micro emboli that may cause lack of perfusion. So in order to measure those particles, we should use alternative technology, which is a counter-culture, for example, or a higher resolution camera and more with a pore, a micropore filter with narrower pores. Was that your question, or?
Yes, thank you.
Okay.
And I have another question, maybe for you and Paul and even Diane. So the NEVA, if I understand, I mean, it's not based on radial force, it's based on drop zones. So it should really capture the clot, it shouldn't penetrate the clot like the Solitaire. So why does it have to have this strong radial force that obviously cause subarachnoid hemorrhage sometimes? Why not make it with less radial force? Because it's not depending on it.
We have actually taken your feedback. So, I mean, I don't have my slides here with me, but I'll show you at the break. The new models that we launched, especially the 5.5 and the 5.5 has the same. It actually has proportionally less radial force than even our smaller models. So, yeah, we always take your feedback into account. So yes, we've actually made the radial force much flatter and a little bit less in our newer models. Thank you.
So if I can just come in there, having worked with you, Tommy, the answer generally from me is, yes, Tommy, I agree. Exactly. Exactly.
I might want to add something there about the radial force because, yeah, it might have the reduced effects on the interferal damage, but and the complications, but also the radial force helps to keep the overall cell structures in place. So in this case, there are some clots that are so tough that the strut of the stent can penetrate. So thanks to this radial force, even that most of the times is not a positive feature, this radial force can help for the indentation.
Mm.
Once the clot is inside, you still want the stent to close the wall throughout the retrievals.
Yeah, and to come back to your point, Tommy, about the sort of the prevention of the microclots, I agree. But I think it's interesting that I know of two technologies that are going to try and prevent this. So you've got the microfiltration net from NEVA, but you also have the what's it called, the DAISY from MIVI, which is also sort of like a preventative tool to prevent these microfilters. And I think it's quite nice to see the evolution of the technique. So like I was saying earlier, it's not recanalization per se, it's recanalization and reperfusion, and that the companies and the engineers and everyone is trying to think about this is actually the most important take-home message, I would say. So any useful feedback on any of these devices probably is useful for the companies, but speak to your IP lawyers first.
Thank you.